Today we study iterative methods of this form. Methods of this form has a long history. I believe over 100 years, but they are still in use in some computations. About this equation, let me introduce two terminologies. The matrix T size is n by n, and I assume real matrix. Let me call this matrix iteration matrix. U0 usually arbitrarily chosen. I give a name to U0. Initial guess to the solution of a linear system. Okay. About this iterative scheme, there are two requirements. First one, we require scheme. I give a name. Number one, we require the iterative scheme satisfies the following conditions. Otherwise, the scheme is useless. Okay, useless. Satisfies. Number one, the iterates UK should converge. Otherwise, the scheme diverges. It is useless. Okay. The iterates UK converge. Okay. Say converge to some point as k approaches infinity. K is the iteration number. Converge to some vector u. Okay, some vector u. Okay. Under this assumption, I let k approach infinity on the both sides. Then we have u left-hand side approaches to u. Right side approaches to u. So we have this equation about the vector u. Also, let me give a name to this equation. Let me call it a fixed point equation. And u, the vector u, of course, is a fixed point, right? Fixed point. Okay. The first assumption, yes, the scheme should converge. Second assumption is we are looking for this linear system. Assume matrix A is non-singular, then the linear system has one and only one solution. This iterative scheme converges. That's not enough. Okay, we also require the fixed point should be equal to the solution of the linear system. Let me denote the solution of the linear system. X star should be equal to X star. Otherwise, the scheme is useless. Okay, useless. Okay. This is a introduction of iterative methods of this form. And let me show you 2 examples. Then I present some theoretical results about this iterative scheme. Okay, 2 examples. Take a look. Example 1. Consider the following linear system. I want to solve the following linear system. Consider 3x1 plus x2 minus x3 is number 3. x1, x2, -1. I want to construct an iterative method to solve this linear system. In matrix form, okay, in AX is equal to B. In this form, matrix A is -1, 5. And the right side is 3, -1, 2. Okay, now, okay, the exact solution of this linear system is the exact solution. Exact solution. I use X star to denote exact solution of a linear system. It is 1, 1, 1. Yeah. Now I want to find exact solution. Let me construct an iterative method. Okay. Starting from this equation. Yeah, starting from this equation. Starting with AX is equal to B. Okay. Then we have X minus AX plus AX. Okay. Let me do that in this way. Okay. X is equal to X minus AX plus AX, right? AX is B. Then take out X. It is I minus A. Yeah, very simple. Okay. This is a physics point equation. A physics point equation. Yeah. The definition is equation of this form. Okay. It's called a physics point. Okay. So this is a physics point. Okay. All right. Now replace the left hand side by U K plus 1. Replace the X on the right side by UK. Then we have an iterative scheme of this one. Of course, T is this is T, and this is C, right? C, right? The C, the vector C here, the vector C. Let me write this matrix equation in detail. Okay. In detail, left side is a vector U k plus 1, first component, second component, third component. I minus a times the vector uk. It is a -2 u1 k minus u2 k plus u3 k, and then plus the first component of vector b plus the number 3. No, in equation form, not in matrix form. Yeah, not in matrix form. This is equal. Now the second equation is -u1 k plus 5 u2 k u minus 2 minus 2 u3 k, and then plus the second entry of vector b minus 1. The third equation, 2 u1 k plus u2 k 4 u3 k plus 2. Okay, now I run this iterative method. Okay, starting with, let me pick an initial guess. Initial guess is say, let me pick. Yeah, we start with u0 with this vector 0, 0, 0. And then run this method. The result is tabulated in the following table. In this table, yeah. K iteration number. K is 0. We have u 0. Of course, the 3 entries 0, 0, 0. When k is 1, k, this is a 0. When k is 1, the first iteration, its entry is 3, negative 1, and 2. When k is 2, the second iteration 0, negative 13, negative 1, and so on. After 10 iterations, when k is 10, u10, we get 571980, negative 4850773. Clearly, this iteration scheme doesn't converge. 11. Yeah. The scheme designed in this way doesn't work. So now let me try a second way. Linear system is here. I solve the first equation for x. Solve the second equation for x2. The third equation for x3 to obtain a fixed point equation. Okay, now let me solve first equation for x, second equation for x2, third for x3. second solution. Okay. Solution 2. Yeah, number 2. Okay. Okay. Then solve the first equation for x, for x1. I get this. 3 plus 1. And x2 is 1/4. Because second equation, x2, I have moved it to the left side, so log x2. All the coefficient of x2 is 0. 1/2 x3. 1/4. X3 is 2/5 x1. Log x3. This is a physics point equation. The left side is x, the vector x. The right side, a matrix times x. Yeah, times x. Because in the second solution, let me use a different iteration, different notation for the iteration matrix. T hat. Okay. Yeah. The first solution, the t I use just t. Okay. Now I use t hat. Okay. T hat. Times x plus c. Right. This is c hat actually. Yeah. C hat. Vector c hat. Vector. Okay. Where t hat is the coefficient matrix. It is 0, -1/3, and then 1/3, 1/4, 0, 1/2, 2/5, 1/5, 0. Yeah. Of course, the vector c now different from solution 1. Solution 1, the vector c is the right side, b, right? Now this time, vector c is 1, 1/4, 2/5. Okay, now let me run this iterative scheme. Okay. Again, I start with 0, 0, 0. Okay. Then I tabulate the result. U 0, of course, 0, 0, 0. U 1, 1.25, 0.4. U2, 1.05, 0.7, 0.5. Okay. And after 10 iterations, we have U10. U10 now is 0.9999. Okay. 0.9999. 1.001. Now this time, it seems that this iterative scheme converges. Okay, converges. 11, 1.000, 1.0000, 1.000. Yeah, this is the exact solution of the linear system. Yeah, exact solution of the linear system. Okay, now this is topic 1. I introduce iterative scheme of sum with some special form. Okay. Then let's turn to theoretical results. Some theoretical results about this scheme. Okay, about this scheme. About is scheme. We have two results. Okay, fundamental results. Let me call the results. Let me put the results into a field. Okay, field. A. Let this be lateral matrix law. What it means? Lateral matrix law. Okay. That means that let A be a matrix. Then the law of this matrix. There are many ways to define a law for a matrix, but defined in this way is called a lateral matrix law. Maximum x ln 0 A times x. Yeah, A times x. X is a vector. A matrix times a vector is a vector. So this is a vector law, some vector law, then divided by the law of vector x. Okay, here, this is a vector law. Law. Okay, yeah. Say for example, if the vector law, if you choose the vector law to be the two law, the Euclidean law, then Euclidean law in this way will imply the corresponding lateral matrix law. Okay, yeah. Lateral matrix law, a law defined in this way is a lateral matrix law. If the iteration matrix T, the law, use this law less than 1, then guarantee the iteration of the iterative method. Let me give a name, say 2 will converge to a facet point U for any initial guess. When for any initial guess U0. Yeah. So if T is small enough in terms of some matrix law, then guarantee this scheme converge and also converge to the solution of a linear system. Okay, the associated linear system. Oh, no, not yet. Just say that converge to some facet point. Okay, this point may or may not be the solution of the linear system. Just converge to some facet point. Okay. Furthermore, okay. Furthermore, when the matrix law less than 1, then the K iteration minus this facet point less than or equal to the norm of the iteration matrix T. to the power k times u 0 minus the limit. Okay, the limit is u. Yeah, minus u. This is the first fundamental result. Okay, whether or not this scheme is converge. Okay, at this point we don't know whether or not converge to the solution of a linear system. Okay. Under this condition, guaranteed this scheme converges to some point. Okay. Of course, different initial guess, the phase point may be different. Okay, may be different. Result 2. If rho t, what is rho t? Spectral radius. Spectral radius of matrix T. What it means? Spectral radius. Yeah, T. I assume it is a n by n. So T has n eigenvalues. Take absolute value on each eigenvalue. Then take maximum. Okay, maximum. Take maximum. Yeah. This maximum is called rho of T. Rho of T. Spectral radius of the matrix T. If rho of T is less than 1, is less than 1, right? Then this iterative scheme, then number 2 is guaranteed to converges to a physics point u. This u may not be the solution of a linear system. Okay, converge. Okay, for any initial guess, u0. Okay. In this case, we have here in part A, we only give an upper bound on the error. Now, in part B, we provide an approximation. Okay, vector result. Okay, UK minus U roughly is some number times spectral radius. This is a number to power k. Then times k iteration number to n. N is the matrix size. N is a physics number, a constant. But k is changing, right? K can go to infinity. Then times u0 minus c. Yeah. Right. Yeah. This is better than this. Okay. Yeah. Here, just give upper bound, but here roughly we have this equation. How about this constant c? Constant c depends on initial guess and also depends on the vector norm you choose. Okay. this is a one direction. If spectral radius less than 1, then this scheme converges for any initial gas. Reversely, is also true. Okay. If number 2, this scheme converges to a fixed point, U for any initial gas. For any initial gas, U0. Then this matrix, its spectral radius must be less than 1. Okay, then rho of T must be less than 1. Okay, yeah. The reverse order is also true. It is also true. Okay, now fundamental theoretical result. Okay, now go back to example 1 and example 2. Let me compare the spectral radius of each iteration matrix. Okay, because we have 2 solutions. Yeah. Solution 1. This is solution 1. Solution 1. Iteration matrix is identity matrix minus this matrix. It can be by computer. Say for example, the spectral radius of this T. What is that? Roughly is 4.9675 greater than 1. So by here, yeah, by part B, when spectral radius greater than 1, low guarantee, the method converges. And also, but this equation is true under rho of T is less than 1. Okay, so that's why the result in solution 1 we see low convergence because spectral radius greater than 1. Then how about solution 2? T hat, yeah, T hat here. Rho of T hat is equal to 0.5. Therefore, by part B of this figure, this scheme converges. Okay, converges. And also, it happens that converge to the solution of the linear system. Okay, in this figure, just say that this scheme converges to some point U, but it doesn't say U must be the solution of the linear system. Okay. This is a topic 2. I still have time, 15 minutes. Let me present topic 3. Yeah, topic 3. Number 3. Also section 9.4. The Jacobi method. The first general iterative method of this form. Okay, yeah, Jacobi method. Yeah. Now, consider the solution of this linear system. Okay, now let me derive a method. Derive equation. Yeah, the ith equation of the linear system is AI1 times x1, AI2 times x2, AI times xi, and then AI I plus 1 times x I plus 1, and so on. Yeah, this is the ith equation. Equals to bi. Okay. Now, because in the previous example we saw that the second solution is convergent. So the method in the second solution to construct an iterative method, how about let's try to generalize it to a general linear system. Okay. This is the ith equation of the linear system. Solve the ith equation for xi. Okay, solve it for xi. Move this term to the right side, move bi to the left side, then divide the equation by aii. Assume aii non-zero. Yeah, then we get this. How about let me use a sigma notation. J from 1 to n. Of course, j not equal to I. Aij xi. Xj not xi. And then plus bi over aii. I can move this number inside the sigma notation. Okay. Negative aii, aij over aii, then xj plus bt aii. Okay. Yeah. Let me denote this number by T ij. Tij is the ij entry of the iteration matrix. And this part, I denote it by Ci. Okay. Ci. Then we have a physics point equation. In matrix form, the equation left hand side is vector x, right side is matrix T, whose entries are defined here. I divide here. Okay. Then times x plus vector c. Now, to obtain an iterative scheme, I replace the x on the left hand side by u k plus 1, and the right side by u k. Yeah, plus the vector c, plus the vector c. The resulting iterative method is called Jacobi method. Okay, this is the Jacobi method. Jacobi method. Actually, this is the solution 2 in the previous example. Okay. Solve the ith equation for xi. But we can derive this scheme in another way. Okay, in terms of matrices. Okay, yeah. Okay. Derive in a different way. Derive is a scheme in a different way. Matrix A, let me split the matrix A into L lower triangular part strictly. Yeah, I should say that this is a strictly lower triangular part of the matrix A. Then pass D. D is a diagonal matrix consisting of the diagonal, the main diagonal entries of A. This is a diagonal part of matrix A. Diagonal part of matrix A. Then plus U, upper triangular part of matrix A. This is a strictly upper triangular part of A. Let me show you one example. Say, for example, let A be 3, 1, negative 1, 1, 4, 2, and 5. Now, I decompose this matrix into strictly lower diagonal plus diagonal plus upper tridiagonal. So this is a strictly lower. Strictly, that means that doesn't include the main diagonal line. So 0, 0, 0, 1, 0, 0, negative 2, negative 1, 5. Yeah. This is a L. Okay. Yeah. The L here. And then D, diagonal part of matrix A. This is D. And U, strictly upper triangular part. So this is one example about this decomposition. Okay. Okay. Now I use this decomposition to derive Jacobi method. Okay. Yeah. Jacobi method. Okay. Now, from this equation, I plug in the decomposition in A. L, D, U. And then we write the left-hand side as L plus U times X plus D. X is equal to B. Move the first term to the right-hand side. Negative L plus U, X plus B. And then assume all the entries along the main diagonal line of matrix A are non-zero. Okay, so I can move D to the right side, D inverse. Plus D inverse. So we obtain a fixed point equation. In this fixed point equation, I replace the X on the left side by UK plus 1. Okay. UK plus 1. Replace the X on the right side by UK. Then this iterative scheme is Jacobi. Jacobi method. Jacobi method. Jacobi method. Yeah. It is this method. Okay. Yeah. Here we derive this scheme by solving each equation. Okay. For some unknown. But here we derive by using matrices. Decompose matrix A into LDU, then obtain a fixed point equation. Now replace the x by UK plus 1 and this x by UK. Yeah, to get Jacobi method. One theoretical result about Jacobi method. Of course, this part is the iteration matrix. This is T, and this part is C. Yeah. How to know this method is convergent and also converge to the solution of the linear system? Have a check with the spectral radius of T. But in practice, usually D size is huge. Say, in general, billion by billion. How to compute all the eigenvalues? That is not an easy job. Most of the time, impossible to get all the eigenvalues of T. Then how to get the spectral radius? I don't have time to present the following result. By using the following result, it is easy to see whether Jacobi method converge to the solution of the linear system. But I tell you next time on Friday. Let me stop here.